Where no one needs any introduction.
Yes, so.
This looks like almost a joint effort within the program.
Yes.
But Jason is, I should draw your attention to the fact that we used Jason's logo, the little knot picture. Did you notice
Oh,
this?
that's right, yeah, I noticed that.
Which we've worked into a little poster, and that's the logo of the whole program. So,
I'm glad I could contribute it.
And this talk, well, there it is, the geometry and topology of random polygons.
Okay, well, thank you very much. So the idea here is the following, right? I want to think about closed space polygons, and this is going to be, in a science context, some model for like a polymer in solution, or something like that, a random filament. And the question is, for me at least, what's the geometry of the space of polygons, right? What's the meaningful geometry on this entire space? And the reason I want to ask that question is because if I want to say what a random polygon is and prove theorems about it, I need a probability measure with respect to sample the polygons. And so these are just definitions, right? So I'm going to focus on, let's see, I'm going to focus on the space of polygons of fixed length, and I'm not going to worry about translation, and shortly I will mod out by rotation as well. And they'll be either in 3 space or in the plane, and they'll be closed.
Yeah, it should be a 2.
Right. That should be a 2.
Why do you choose length 2?
It's going to be natural with respect to my construction. But, you know, length 1 would be the same. There would just be a scale factor somewhere.
Length, the length, this total length of the
total length
yeah.
of the polygon. Now, I should say this isn't a fixed edge length measure, so they're not equilateral. The edge lengths obey a certain probability distribution that will work out a little later on. So, okay, so let's think about this for a moment. So you can't understand closed polygons until you understand open polygons. So those are polygons that I call arms, right? So arm space is, again, the space of n edge polygons of length 2, but this time they're not required to close. So one thing that's worth saying is that if I want to think about the moduli spaces, if you mod out by rotation, they look like the following. There's an SO3 action on arms in space, and there's a moduli space under that, which we'll call arm hat. So that's arms up to rotation and translation. And then downstairs in the plane, there's an O2 action on arms and a corresponding moduli space. And it'll be important that it's O2 rather than SO2. Right.
Armageddon, you said it's Armageddon, I was going to say. It is not closed.
Not closed.
It's a novel concept to me, a polygon that's not closed.
Well, think of it, the motivation is people talk about like the robot arm problem, right? Yeah. So you have this chain of linear effectors or something.
It's just a terminology. So a polygon for me is a closed.
I understand, right. So yeah, I should say polygonal line or something, or PL line. So if we think of our plane guys as sitting in a plane in space, well then there's an SO3 action that reflects the plane, right? So if I'm going to include this little moduli space in the bigger one of space polygons, it has to be a moduli space by O2 and not SO2. Okay, so here's the big idea. I'm going to use quaternions, being in England, and loving all this stuff. It'll turn out that if we write things quaternionically, it will give a really nice construction for closed polygons, and it'll make the closure constraint easy to understand. So, so remember that quaternions are given by 4 coordinates. There's a real part and then 3 different complex parts, I, j, and k. And that if I write down the following quadratic form on the space of quaternions, just take your quaternion, multiply on the left by the quaternionic I, and then multiply on the left again by the quaternionic conjugate, which just, as before, reverses the sign of all the imaginary stuff. Then this thing gives the Hopf map. And that gives these 3 quadratic polynomials in the 4 coordinates, which turn out to have like wonderful geometric and topological properties. So one of the nice ones is that the norm of this 3 vector is the square of the norm of this 4 vector in Euclidean space. So that'll prove important soon. And then one thing we can do, right, is take a point in the unit sphere in quaternionic n space, so that's n quaternions, apply the Hopf map to each one and get a set of n vectors in Euclidean space. So that set of n vectors are going to be the n edges of my polygon. And I can just assemble them into a non-closed polygon, a polygonal arm. So then I can define a measure on arm space by pushing forward the measure on the quaternionic sphere using this map. So the nice thing about this measure is that, of course, the quaternionic sphere is a symmetric space. It's invariant under the full symplectic group of quaternionic matrices or hyperunitary matrices. And so that will give a nice action on arm 3 and a nice measure that's invariant with respect to that action. So
SO3 pushed down. So it pushes down the SO3 invariant measure.
It's not SO3 invariant yet, but it will be shortly. SO3 invariance will mean something natural here. So, in fact, let's talk about SO3 invariance now. Right. The interesting thing about quaternions is that they also represent SO3, right? Like unit quaternions represent rotations in 3 space. And they do it by this version of the Hopf map. Take q bar iq, q bar jq, and q bar kq. And those are 3 orthogonal vectors. That's an orthonormal frame in R3, as long as this is a unit quaternion. And the Hopf map obeys this interesting kind of equivariance property with respect to that construction. So if I multiply on the left by right, if I multiply on the right by a unit quaternion p, that's the same thing as rotating the Hopf image of Q by the SO3 element framed Hopf applied to P. So what does that mean? Well, that means that right multiplication by a quaternionic scalar, a unit quaternionic scalar, is SO3 rotation of the resulting polygon downstairs, which means that the space of polygons up to rotation isn't the quaternionic sphere. It corresponds to the quaternionic projective space. So that's this diagram, right, which says that quaternionic projective space projects by the Hopf map to arm space modulo the SO3 action. So that's actually kind of delightful, because now I have a chain of spaces that I do understand, the unit quaternions, which are just a copy of S3, the 3-dimensional sphere, the quaternionic n-sphere, the moduli space, quaternionic projective space, and downstairs, the spaces I want to understand, SO3, ARM3, and ARM3 mod SO3. Okay, so now we have to figure out how to get closure into all of this. And again, the algebra of the Hopf map will kind of save the day. But first, before we do that, I want to talk about how planar things fit in. Mostly because it's really nice. I don't know any really good science application for a planar polygon, right? I mean, maybe like Giovanni's planar DNAs, which are now planar random walks of some type with random crossings and so forth. But if any of you know a really good science application for planar random closed loops, I think we'd love to hear it.
In the old days, it was locomotives.
So, okay, so the question then is, how does this restrict to planar arms? Okay, well, in the first place, what is going on with the Hopf map? Well, consider there are a pair of planes. There's 1 plus j, that's a copy of the complex plane inside the quaternions. 1 plus I is the obvious one, but 1 plus j works just as well. And there's also I times 1 plus j, which is the ik quaternionic plane. And again, that looks like a copy of the complex plane. So the Hopf map sends each of these to the ik plane. So there's the calculation. And what's interesting is if you have a plus bj, it gets sent to something plus something else. But if you have ai plus bk, the same two real coordinates get sent to the reflection in the ik plane, something minus something else. So that is where the O2 is going to come in. Here's the reflection action. Okay, so what this tells you is that I can rewrite this in the complex form. So we'll say that if I write the complex number a plus bj, then Hopf of that complex number is actually just I times the square of z bar, the conjugate. And Hopf of I times the complex number, that's in the ik plane, is just iz squared. So when you restrict to these complex planes, the Hopf map is just squaring the complex number. When you work in quaternions, the Hopf map is this more complicated thing I gave a slide ago.
Jason, here's a quick comment. So
Yeah.
if you multiply on the right by minus I, you got so it's not quite the same thing. But never mind. I'll save it for later.
All right,
It's gonna give
we
you
can work this out later. Yeah. Okay, so what we've learned is that if we want to think about plane arms, there are two copies of complex n space inside quaternionic n space. There's the sort of 1 plus j complex n space, and there's the I plus k complex n space. And the Hopf map takes the unit sphere in each of these copies of Cn onto planar arms. And then we can see how SO2 fits in here. SO2 is real stuff inside SU2. And to add an element to get O2, we add this quaternionic matrix, this element of SU2. And the effect of this is to swap the 1 plus j and I plus k planes. So this action is going to descend to the reflection in the plane containing the polygon. So here's the final diagram for planes. Upstairs we have a copy of O2, well, SO2, real 2 by 2 matrices in SU2, together with this special eta matrix. We have two copies of the complex n sphere, both mapping down onto planar arms. And the moduli space is two copies modded out by this O2, so either acting coordinate-wise by SO2 or swapping the two spheres by the action of the eta matrix. And downstairs we get arm2 mod O2, which is our arm2 hat. So the beauty of this is sort of an equivariant model for space polygons and within them plane polygons. Okay, so here's the whole picture, right? So it's sort of frightening commutative diagram, which shows you that upstairs we have complex spheres, the quaternionic sphere, complex spheres mod this O2 and quaternionic projective space. And downstairs we have planar arms and space arms and their corresponding moduli spaces. Okay, again, if we want to take random things, the idea is going to be to sample upstairs and project downstairs.
Tell us how big the fibers are, how bad this is multiple to one.
Oh, the fibers are interesting. So the fibers for, they're big. They're generally n tori, and the fibers represent a framing on the polygon. So if we did the coordinate-wise Hopf map to get the edge vectors, q bar I q, well, if we had done q bar jq and q bar kq coordinate-wise, we would have gotten not just a chain of edges, but a chain of frames, right? And they would have been orthogonal frame, orthogonal frame, orthogonal frame.
Oh, on the edges, the framings are on the distinct edges.
That's right. The framings are on the distinct edges. So then that means that over every polygon lies a sort of n torus of possible frames on each edge. Right? A little degenerate if you have an edge of length 0 or something, right? Okay, so now what about closed polygons, right? Well, here's a new set of coordinates. If I have the sphere in 4n space, I can write it as the join of spheres in 2n space. So specifically, that construction is take a vector in one unit sphere, a vector in the other unit sphere, and combine them with cosine and sine, right, to get a vector in the larger 4n dimensional space. So this J has the effect of moving the complex n space from the first two coordinates to the second two coordinates. So this is now a vector in the quaternionic sphere. Okay, well, fair enough. I can write any sphere like that. Usually you write the 3 sphere, right, as the join of two 1 spheres. But now what I want to do is focus on a submanifold of that, which is going to be u and v in complex n space and the angle pi over 4. So it lies in the kind of Clifford torus in S in the quaternionic n sphere. That's the middle torus. And we're going to take pairs such that u and v are Hermitian or orthonormal. They're just perpendicular. So that's the Stiefel manifold of 2 frames in complex n space. And then the beautiful insight, which is due to algebraic geometers, due to Knudsen and Hausmann, is that this maps down to closed polygons under the Hopf map. So the identification is Stiefel manifold is framed polygons, project downstairs, you get unframed polygons. Now, here's the cute part. Here's SU2. That's just like a copy of SP1, the quaternionic scalars. It acts on the complex 2 frame by rotating it by that 2 by 2 matrix. And it acts on the polygon by rotating the polygon in by the element of SO3 corresponding to that entry in SU2. So SU2 double covers SO3, so there are 2 different ways to get the same SO3 rotation, but I don't think it actually matters in practice. So you get this, again, like really nice kind of equivariant diagram. So here are spaces I like, SU2, the Stiefel manifold mod SU2. And here are spaces I want to understand, SO3, closed polygons in 3 space, and the moduli space of closed polygons up to rotation. Now remember, these are already up to translation, so this is mod the full Euclidean group. So shapes of polygons. Okay, so why, right? Well, it's a calculation. So if you look at the Hopf map written in this complex form, what you get is that the I component of the vector is the difference between the norms of these two complex numbers. And the j and k components are the complex product a times b bar. Right? This is just a feature of the 3 quadratic polynomials I wrote down earlier. So if you write this down, well, and sum it over each coordinate, right? Sum it over ai's, which are, remember, cos theta ui's, and bi's, which are sine theta vi's, then what you get is the sum of these guys is the norm of the complex n vector A squared. The sum of these guys is the norm of the complex vector B squared. The sum of these guys is the Hermitian inner product of the 2 vectors A and B. So if these things are going to vanish, that is to say, if the sum of the Hopf images of all these quaternions is going to be 0, if the polygon closes, then these complex vectors, cos theta u and sine theta v, have to be orthogonal, and they have to have the same norm. That's only going to happen if cos theta is equal to sine theta. That's the angle being pi over 4, since u and v are unit vectors to start with. And u and v are orthogonal, because there the scalars don't matter. So this tells you how the closed things sit inside the arms. They're a submanifold of the central torus in the quaternionic n-sphere determined by this orthogonality condition. Okay, well, okay, fair enough. So we get again a nice diagram. I won't take you through how planar closed polygons fit in, but they're real Stiefel manifolds. So complex Stiefel manifolds are space polygons. Real Stiefel manifolds are plane polygons. The moduli spaces are Stiefel manifold mod SU2 is almost a Grassmann manifold of 2 planes in complex n space, but it's actually a circle bundle over the Grassmann manifold. If it was V2 mod U2, it would be the Grassmann manifold. Downstairs, we've got closed polygons and the moduli space, and closed plane polygons and the moduli space.
So what's the extra U1? Is it like a parallel frame? It shows you the parallel frame.
The extra U1 simultaneously rotates all the frame vectors together.
So it's like a parallel.
So
frame.
yeah, it's like a choice of like which parallel frame you take, right? So the bishop frame or something exists in the Grassmann world, but not the V2. You know, see, the bishop frame is uniquely defined in the Grassmann world, right? But it's not uniquely defined in the V2 mod SU2 world, right? Because that requires you to actually know the starting vector.
Jason, did you say what G2 is?
Oh, this is the Grassmannian. So this is the Grassmann manifold of 2 planes in n space. So that's closed planar polygons. They project from the Grassmann. Okay, so now what? Well, okay, our basic idea here is we're going to find this measure on random polygons, and we want to compute things about it, right? So We want to know, for instance, what's the expected value of total curvature of such a closed polygon, or the expected value of radius of gyration, or the expected length of the chord skipping 17 edges, or how close a short section of a closed polygon is to the corresponding section of a non-closed polygon, right? So if you want to get hard bounds on all these things or calculations, you start with the measure. And now we're going to do integrals over the symmetric spaces up top and get probability results on the polygon spaces downstairs. And that turns out to be fairly powerful. So first we work out the PDFs for edge length. So they're all given by beta functions, as it turns out. And there are the particular things. The proof is a nice computation. It's kind of fun. And we can see it, right? So this is the lengths of space arms, right? It has to end at 2 because the length of the whole thing is 2, right? So for a single arm, here's the probability distribution. This is 4-edge space arms, 5-edge space arms, 10-edge space arms. So you can see that these distributions are getting narrower and it's getting shorter, right? Because of course, if you have a 10-edge arm, you expect in some larger sense, the average length of a segment to be 2/10. Okay, now what if they're closed? That actually changes the distribution quite a lot. So for space triangles, the probability distribution is this. It's linear, right? No one edge of a space triangle can be longer than 1, right? Because it has to close. These are length 2. Here's 4-edge space polygons, perfectly symmetric. 5 edges, you can see that it's starting to tail towards 0, 10 edges, 15 edges. And again, they're getting narrower and compressed towards 0. After all, these things are getting short. Here's plane arms of 3 edges, plane arms of 4 edges. So in the plane, you notice this interesting thing, which is that it doesn't go to 0 again, right? So for plane arms, the chances of getting a 0 length edge are larger. Okay, here's planar triangles. It has this funny distribution. This is my favorite, planar quadrilaterals. So in our model, or planar quadrilaterals, which are the very special manifold G2R4, right? 2 planes in 4 space, which is a manifold that everyone loves for any number of reasons, has the uniform probability distribution. So the distribution of edge lengths is exactly flat. So I think you can probably prove neat things about, or reprove neat things about planar quadrilaterals, like Ptolemy's theorem or something, from looking at the geometry of G2R4, you know, which is like a silly thing to do, but not if you love plane geometry. So here's 5-edge plane polygons, 10-edge plane polygons, 15-edge, and you can see that they're sort of going to the space distributions, right? They're going to the plane arm distributions, right? They still have a non-zero value at 0, but again, they're getting pushed to the left-hand side. Okay, so what does this edge length distribution tell you? Well, here's an amazing fact, also due to Ken and Laura Zerbal. If you have a measure on a polygon space or an arm space which is invariant under reordering the edges, which is certainly little enough to ask for, then the moment of the edge length distribution determines the expected value of all squared chord lengths, right? So squared chord length skipping some number of edges, the expected value of radius of gyration, and the expected value of the dot product of any two edges. So I thought it was kind of amazing that you could get all this just from edge length under this rearrangement symmetry. But here's our proof, which is, I guess, slightly different from Ken's proof in that it's in our language. So if we let this chord be the length of the chord skipping the first k edges, so chord 1 is an edge length, chord 2 is skipping 2 edges, and so forth.
Squared length or the length?
Squared length. Squared length. Then you can observe that if you take all the polygons that I could construct from a given set of edges by rearranging them, and I take the average of this chord function over that ensemble, over that finite ensemble, then in fact there's a really nice expression for the chord length, which is a sum of all the squared edge lengths, the squared length of the failure to close vector, and these quadratic polynomials in the number of edges you skipped and the total number of edges. And the point somehow is that if I take, guys that skip the first 3 edges in one polygon, well, I have to worry about how those 3 edges compare to the other n-3 edges that you're not sampling. But if you symmetrize over all rearrangements, then those 3 edges could be any 3 edges. And in fact, every triple of edges shows up. So if you do the sum and reduce, all the weird cross terms eventually drop out, and you're just left with this, something that has to depend only on things that are themselves edge length rearrangement, edge rearrangement invariant, like the sum of the edge lengths and the sum of the length of the sum of the edge vectors. So here's an example, right? These are all rearrangements of the edges that make a regular pentagon. These are all rearrangements of a bunch of unit length edges which don't make a regular pentagon, but which make this. So by the theorem, since these are closed, the L, the failure to close, is 0. Since they're equilateral, all the squared edge lengths are the same. So these have to have the same average chord lengths when you average over this ensemble and this ensemble. And there's the plot, right? The pink guys are for the regular polygons. This is a histogram of how many times each length occurs. The blue guys are from the irregular ones, and indeed, the average over each distribution is right here. So now we can work out the moments of all our edge length distributions. They're beta functions, which is maybe not surprising because I integrated beta distributions to get them. And so in particular, I know the squared edge lengths by plugging in p equals 2 in these formulas. So now you can work out the expected values for chord length. Here they are for arms, polygons, plane arms, and plane polygons. And you can see that while this increases with k, the further out you go on an arm, the further on average you are from where you started. This increases in k for a while and then decreases in k. So the further you go around a closed thing, well, eventually you start getting back to where you started. Here is samples of 5 million, 50 million, I forget. Yeah, do you remember? Okay. Samples of a few million 500 gons. Those are the dots versus the prediction, right? I'll talk about the sampling algorithm in a minute. But certainly the data looks good. These are samples of a few million 500 edge arms in the plane and in space, again, versus the theorem. And so that looks good for the sampling algorithm. And now you can compute radius of gyration as well. That's the average squared distance between any two vertices. And you get the following kind of neat result, that asymptotically, the radius of gyration for a closed polygon is exactly half the radius of gyration for the corresponding arm. Right? So here in the plane I have 4/3 and 2/3. Here in space I have sort of 1 and 1/2. So for a closed thing in space, the radius of gyration is like 1/n. So here are, again, samples versus theorem. And you can see that it works. And then, in fact, the equilateral polygons are also rearrangement invariant, right? Unlike any other fixed edge length space, right, where rearranging things won't keep you in the same edge length space. So if I average over those spaces, I get these results. Again, gyradius halves when you close the polygon, right? Again, the further you go out on an arm, well, it goes up, your expected chord length goes up for a while and then goes down as you come back home, right? Interestingly, for plane and space equilateral things, the results are the same. So that's why these say arm I and pol I. They don't depend on whether it's in the plane or in space. Okay, so you can compute, I should have changed this.
But that's
Right.
not the case, that's for the equilateral ones, but for the...
That's for the equilateral ones. For the non-equilateral ones, it makes a difference whether you're in the plane or in space.
Is there a geometric sort of Grossman picture for those?
Well, the reason is essentially that you're not quite comparing apples to apples, because the way we constructed our plane polygons, they were implicitly framed by the normal vector to the plane. But our space polygons could be arbitrarily framed. So if you wanted to compute space-framed plane polygons, it would look much more alike. Okay, so here's the variance of edge length. It's going down, but not fast enough. So it's going down quadratically, but on the other hand, the edge length itself is going down linearly. So this is not going down fast enough for the thing to be becoming asymptotically equilateral. What it is doing is becoming asymptotically short-edged, but that's not surprising because the length is fixed at 2 and I'm adding more and more edges to this thing. Okay, so here's the sampling algorithm, and this, like in a science context, is really the point of all this, right? So how do you sample closed polygons? Well, it's not trivial because I can certainly pick edges independently, but they won't close. So how do I pick edges in such a way that I'm enforcing the closure constraint but nothing else, right? I'm not introducing any spurious correlations between the edge lengths. And the answer is, if I sample on the Stiefel manifold uniformly and push down, I'm sampling closed polygons uniformly. So how do I sample uniformly on a Stiefel manifold? How do I generate a uniform orthonormal 2-frame? Well, it's easy. Just generate 2 vectors on the sphere uniformly and then orthogonalize them with Graham-Schmidt. And that gives you a uniform distribution on frame space. So that's this code, which is short, right? How do I sample on the sphere? I take each coordinate to be normal, right? That is a UN invariant distribution on complex n space. So if I rescale a point from that distribution to length 1, it has to lie uniformly on the complex n sphere. So then I do that, And then I just apply Graham-Schmidt to two of those random complex vectors. And then I apply the Hopf map. So here are some pictures. These are random 20-gons. These are random 200-gons.
What you're showing is if you took the Brownian path in it, just before Brownian,
Well, that's a
jumping.
collection of polygons, right?
Yeah, I'm saying, so there's you're jumping around now. You just sample.
Yeah, I'm just jumping around. So these are directly sampled. So these are this is not an ergodic process like
Right.
crankshafts or hedgehogs or something. This is direct sampling from the probability space. So, you know, it's quick, it's linear time, and you just get what you get. These are guaranteed to be perfectly sampled, at least if your original normal variables were well generated. So, and then you can generate 2,000 gons too, right? And we've generated, Clay made a nice picture of 1,000,000 gon. So you can see that they're looking increasingly kind of fractal as you continue to add edges to the polygon. So I think this is actually what things look like in space. I mean, what, you know, sort of random polymers look like. I have a student who proved the interesting theorem that if you look at inscribed polygons in this, right? So you say, pick k edges out of an n-edge polygon. So pick 6 gons in here, or pick, you know, 500 gons in here. Then they're not sampled according to any distribution that looks like this. In fact, they're very close to being sampled according to the uniform box distribution, where you just pick points at random in a volume in space and connect them. So I think that's telling you in some sense that this polygon is becoming space filling in a certain way, right? So it should be possible to compute the fractal dimension as this process goes to infinitely many edges. And I have a student working on it. And I'll sort of report as we know something.
Could you also look at the knot type
Yeah,
distribution?
so you can certainly look at the knot type distribution of that, and that's an experiment that we intend to do, but we haven't done yet. We've been, you know, trying to prove like a Summers-Whittington kind of theorem for this, that, you know, all but exponentially few of these things are knotted. Of course, the Keston pattern methods don't apply directly, but we think you can come up with a proof along the following lines. A short segment is provably close to a short segment of arms in PDF. A short segment of an arm can be a knotted ball-arc pair with some non-zero probability. And there should be enough short segments that are kind of isolated that, you know, nothing comes back to them from far away, that a knotted ball-arc pair there would imply knottedness globally. But we haven't, you know, we haven't actually pulled that off yet. But we're working on it. We certainly believe it to be true.
Sure, it looks true from that picture. Yeah.
It looks true, right? And what it looks like is you can see sort of compositeness in this,
Yeah,
right?
lots of little local knots. Yeah.
They'll make local knots here, and then that'll be sort of obviously a connect sum with, you know, some other region of local knotting.
Is the clustering a focus, is the clustering a consequence of the choice of projection, or is there actually kind of anomaly, there's some kind of Poisson
Oh
thing?
no, there's actually some kind of like
There's spatial
clustering in there.
Which is out of the distributions. Right.
Yeah, we've rotated these, and looked at them quite a bit, and what you tend to get is some number of spatial blobs where it's kind of dense, connected by stretched out regions. And I don't have a really good explanation for that yet, other than...
I just noted, because Giovanni had the same picture, basically.
Yes, it's right, and this shows you somehow that, like, you might not need self-contact or something to explain Giovanni's picture, at least explain part of it, right? It may just be that, generally speaking, you tend to get blobs and loops from a random
See the
polygon.
same picture with the random walks, where you have actually unit length steps in space. See exactly the same picture.
So you hang
There, I
around for a
think the
while and then you
argument-
leave.
Pardon?
You hang around for a while in a region and then you leave, and
Yeah,
then you
it's
hang
the
around
growth
for a
of
while.
the sort of end-to-end distance. So you know what that looks like for subsegments, and so you see the same sort of structure there. And I think that and another little trick or two is what Yao uses to prove the theorem for three-space random walks, random polygons.
Yeah,
equilateral.
equilateral.
Right,
Yeah,
equilateral.
yeah. I think,
Gaussian
and
and distributed
Or
edges.
Gaussian.
or Gaussian distributed edges. So these are sort of neither, right? They're not Gaussian distributed edges, and they're
Right.
not equilateral.
But you do have the growth in the end-to-end distance of
Mm.
subsegments, which is a key factor, I think.
Yeah, I think that's right. And you have the same property that like an arm tends to be closed, or almost, an arm tends to be almost closed. And the reason is somehow that if you select two complex n vectors at random from a high-dimensional complex sphere, they're almost always orthogonal, right? Or almost orthogonal. Because the chances of getting some, what's a dot product? It's a correlation, right? Well, the chance of getting some non-trivial correlation between this random chain of 200 Gaussians and some other random chain of 200 Gaussians is very small. So that's sort of telling you that, over say 200 edges, it's kind of expected to come back to almost where it started. So it's sort of almost closing and then leaving, and then almost closing and then leaving. So you can see, right, all of these 2000 gons have these kind of blobs and walks, right? And you can almost convince yourself that you see little local knots in here. We have not computed the distribution of knot types, but this is an experiment that's very much on our radar to do. So here's a really interesting question about this, right? So Ken and Eric noticed when they were taking random equilateral polygons that if they computed total curvature, they got an expectation of the number of joints times pi over 2. Well, that's believable. A random pair of vectors on the 2 sphere is this average angle pi over 2, plus this interesting contribution, right? 3 pi over 8, plus smaller terms.
What's the curvature of an n-gun?
Okay, so that's the sum of the turning angles. So the
It's in three space.
in 3 space. So it's the sum of the exterior angles at each vertex. So in our model, it turns out to be, there's the same sort of surplus, but the surplus is pi over 4 and not 3 pi over 8. So certainly we can do many polygons and get many digits of pi over 4. So it really is pi over 4. And I say open star because with Grossberg and Kussner, we have an argument that we believe gives you this asymptotically. And so, but I think it's a neat question. And it turns out that the pi over 4 is a natural consequence of the way our edge length distribution works out compared to the edge length distribution for equilateral things.
This pi by 2 is just that it's the most, sort of the most likely.
Yeah,
It's
that's
the
right.
average.
It's sort of the most likely, yeah.
It's just basically the average.
Mhm. But of course, if it closes, it has to bend a little more than that, right, on average, because you went out, so now your chance of coming back is a little more than your chance of going
So that's
further
where
out.
the next term comes from.
That's where the next term comes from. And then after that, it's something of a mystery. I mean, I think we can write an explicit integral involving Bessel functions and things for the over R3 for the distribution for any n. But that's not quite the same as knowing, you know, having an integrand is not the same thing as having an integral.
What's this big O1? I'm confused.
That just means terms that go to 0 as n goes to infinity. So,
Big O1? I thought it meant less than a constant. It means a
It's
little.
it's a little low.
It's a little.
oh, sorry, yeah.
Okay, so-
Yeah, sorry, not terms less than
It's
a
not
constant.
big.
That should have been a little
Big
low.
L1,
Right.
Yeah, okay, yeah. So
Yeah.
Big O1's not a good estimate.
Right, yes, true, certainly true. It's not a good estimate
Smaller
for
and
the
smaller.
constant, yeah. So,
The smaller than little o1, this means little o1, doesn't
yeah,
Yes.
terms in little o1, right,
it? Yeah.
is what I want to say. Okay, so here's a question that has come up before this, and I'd love to talk to everyone about it, because we're still formulating our ideas about it. But, you know, Ken gives these great talks about the knot type of open curves and so forth. So I want to ask a related question, which is that I guess I sort of claim morally that an algorithm for determining the knot type of open curve should be good at recovering the knot type of part of closed curves. So if I take a closed curve, which really is a knot with a real knot type, right, and I delete part of it and I hand you that much information, whatever your definition of open knotting is, it should be good at recovering the knot type of the original thing. So from that point of view, I claim that it's a statistics problem. You know, getting the best algorithm on average is a statistics problem. So you want to sample the space of all closed polygons conditioned on whatever you know about this closed polygon, which is, you know, I have some of the edges. So I claim to you that if you have k of the edges, then what you know is the failure to close, right? So the other n minus k edges have to get back. And you know the length of the other the other n minus k edges, because you know how much length was taken up so far. And you know n minus k because I'm assuming you knew which polygon space you had a partial polygon from. So with all those assumptions, I think that the conditional thing is basically the space of arms which fail to close by a certain length and have a certain length. And if that's true, then I believe there's a sort of general theorem that says sampling in this space and closing the polygon and computing the knot types of all those closures is kind of the unbiased estimator for knot type. So it's, in an average sense, the best you can do. So the algorithm would be, this is a sampling algorithm for arm space. You generate a closed thing and then an orthonormal frame, and then you rescale the two vectors appropriately. So that gives you something that fails to close in a particular direction by a particular amount. you rescale it, and then you close your original guy by this new random arm, and then you compute the knot type, right? And you do that over zillions of samples. So with Eric, we have the plan of, I don't know, with Eric et al., I should say, with the Rodden crew. So we hope to start some experiments to compare this algorithm to like ray closure and fix the endpoints and tighten the tube and directly close it and a few other ideas. And we just want to see which of these is best at recovering the original knot. Right, and also I think as a function of how much of the knot you know, right? So I suspect if you have n-1 edges of an n-edge knot, all these algorithms are pretty good at recovering the original knot type. But you know, if you have n over 2 edges, then that's a very interesting question.
But so it's really good if you know your knot's equilateral, but if you don't know, if you only know the total, well, if you know the total length, then you know what's missing.
Mm-hmm.
Yeah, then you,
Yeah,
okay.
if you know the total length, you know what's missing.
Right.
That's my claim.
Yeah.
That's all I'm saying, right? And another good thing about this is, or another, I don't know that it's good, it's probably a bad thing about this, but another thing about this is that, you know, the examples that people like nice, smooth, partial trefoils and stuff, this may perform very badly on because that's an extremely unlikely random n-gon to begin with. So, you know, the fact that it does well on random knots, you know, that look all squiggly and fractal does not mean it will do well on knots that people pick randomly. You know, I'm reminded of a story that Eric told me that he was listening to one of these climate science talks at his university about tornado modeling, and they had various statistical estimators for when there's going to be a tornado. And the best algorithm for predicting tornadoes was no. So that was way better than anything they'd come up with. So it's entirely possible that the best algorithm for predicting closures of a random knot is unknot, right? Or connect some of a couple of trefoils or something, right? And that's what you're going to discover from doing this. But that's why we do the experiments, right? Here's some other open questions that I really like. Oh, and I didn't even, here it is. So here's one of my favorites, right? What about lattice polygons? So lattice polygons in this model are vectors in a Stiefel manifold whose individual coordinates lie among a certain number of possibilities, right? So this is like one of those interesting geometry, like number theory kind of questions, right? So you can think of it like the following question. Take an sphere in n space, like big sphere, right? And ask how many points on it have integer coordinates, right? And ask whether the set of points with integer coordinates sort of is uniformly distributed on a big n sphere, or whether it, you know, is patchy, does it miss some things? And number theorists love to prove results like, you know, this distribution of mass is completely uniform on the n sphere for large enough radius and so forth. Right, so if I could get them to prove a similar theorem for Stiefel manifolds, right, frames with integer entries, which are big in high dimensional space, are uniformly distributed over the Stiefel manifold, then that would be a neat theorem because it would say sort of that lattice polygons uniformly fill the space of random polygons, right? So, which I think would be like a neat connection between these two models. And again, I wanted to ask you guys about this because I don't know any other theorems about, say, the relationship between lattice polygons and off-lattice polygons in general, right? Like, if you connect every 1,000 vertices in a lattice polygon? Do you get an off-lattice polygon that's somehow randomly sampled?
So lattice polygons means there's something in the equivalence class that has rational vertices. So what a lattice polygon is.
I guess I mean they're on some uniform cubic lattice, right? So if you want to say rational vertices, I would want to fix the denominator.
Right, well, so
Right.
so you're getting into equilateral.
Well, that's another question,
I think
right?
that's what you were getting at.
Is that-
Avoid equilateral. but-
No, not at all, I just didn't know the definition of
Yeah.
lattice polygon.
Okay,
I just-
let me interpret what you're saying,
Yeah.
is to avoid an analog of lattice that isn't occurring equilateral, so that would be restricted.
Right. Well, yeah, I mean that's actually another question which is interesting, which is that if you take a random equilateral polygon and you connect every 500th vertex, right, in an equilateral random million-gon, what's the distribution on edge lengths? You know, what polygon is that, right? Like what non-equilateral polygon is that polygon space is that sampled from? And in particular, is it sampled from something like this space or some other one? Okay, the paper is up and accepted, and we would love to talk to you guys about such things. Thank you very much.
Well, we've had a few questions already, but are there any more? Many questions, one could.
Can I try the Brownian question?
Yeah, go ahead.
So you guys do a lot with this crankshaft thing, and so I'm just curious, that the sample pictures you were showing, you were jumping all over the space, and so what I was curious about just is whether the measure up on Stiefel variety space, if you use that as a guide to how to, or the geometry maybe, not even the measure, the geometry of it, to make small changes there.
Right.
You know, whether as a sort of natural kind of diffusion process for the thing rather than just jumping around. But
Well-
like a Brownian path of.
Yeah, I mean, I think you can certainly study Brownian motion on Stiefel manifolds. I mean, that doesn't seem too hard to prove some things about. You know, there's the more general question of the fixed edge length spaces, and in what sense, say, crankshafts are an ergodic path on, you know, how fast the diffusion is, right? Like, you know. And I should say that, you know, I've cast aspersions on crankshafts before, but I now believe, you know, that it does converge to the correct measure. So the question is really just how fast does it converge? So it would be nice to understand the fixed edge length spaces from this point of view and to prove a theorem about, you know, how many crankshafts you expect to do before you get uniform sampling for some, you know, measure of uniform.
Jason, can you remind me whether it's the crankshafts or the sort of folding of polygons that gives you this symplectic structure?
Folding gives you the symplectic structure.
So there are two ways, two ergodic ways of sampling equilateral non-space. One is by taking two vertices and folding them, and the other is by literally taking edge vectors, pair of edge vectors, and rotating them around an axis, which is sort of more like the way an automobile. That's a crankshaft. There are two different ways, and the folding one naturally fits into this context, I think. And the crankshaft doesn't, but I think what you mean by crankshaft is fold rather than really crankshaft. What do you think?
I'm agnostic.
Agnostic, okay.
No, I mean, so yeah, I mean, well, go ahead.
Well, no, I mean, okay, so I think the actual truth somehow is that these are two different Hamiltonian vector fields, right, for two different functions, right? So like the folding is the Hamiltonian associated to the chord length, right? And the crankshaft is the Hamiltonian associated to the vector sum of the two vectors that you're crankshafting around. So, you know, each one is a Hamiltonian flow with respect to that symplectic structure and has volume preserving and so on and so forth. Right, and in fact, all of these things that, you know, that people have proposed that I know about seem to be Hamiltonian flows, you know. There's in fact a really nice one based on the triple product of a triple of vectors, so the Hamiltonian flow associated to that. It has the beautiful property that it keeps planar polygons planar. So that's actually an ergodic sampling algorithm for planar equilateral random polygons.
This ergodic Hamiltonian flow thing gives me problems because it's very hard to prove a Hamiltonian flow is ergodic.
Well, it's not a single Hamiltonian flow that's supposed to be ergodic, right? It's go along one Hamiltonian and then pick another function and go along that Hamiltonian. And then,
If your sampling is chosen from the right measure, but
yeah,
ergodic process.
yeah. So yeah, I agree. A single Hamiltonian flow would essentially never be ergodic. But the point is, there's a collection of them, and you hope to use that as a kind of basis.
Well, perhaps we continue the discussion over lunch.
Yeah, all right.
Thank you very much, Jason.
Thank you.